Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at day 2 of our 8.2.1 lesson for exponents and scientific notation. This one, I promise, will not be as long as day 1. There was a lot of stuff to get to in day 1, so I apologize, but it was important information. All right, so let's move on to applying scientific notation and how all this works. When astronomers describe distances in space, often the numbers are so large they are difficult to write. For example, the diameter of the sun is approximately 1,390,000 kilometers. To make these numbers, or these large numbers easier to write, astronomers and other scientists use scientific notation. In scientific notation, the diameter of the sun would be written as 1.39 times 10 to the 6th power kilometers. So rewrite 10 to the 6th as a single number without an exponent. What would that number be? And then what happens when you multiply that number times 1.39? Well, first off, 10 to the 6th power means that it has 6 zeros, right? So that would be equal to 1 million in standard form. And what does this mean if you multiply 1.39 times a million? Well, 1 times a million is a million, so this has to be 1.39 million, correct? But if we're going to write that in standard form, what we learned or talked about in previous lessons, especially in yesterday's lesson, is you would move the decimal 6 places to the right. And so that's how you end up getting 1.39 times 10 to the 6th. The decimal would normally be here, but you go 1, 2, 3, 4, 5, 6, and then it goes there. So it ends up being 1,390,000. So in scientific notation, the mass, how much it weighs, the mass of the sun is 1.99 times 10 to the 30th kilograms. What does this number mean? Okay, it says discuss with your team, but just think about how to write this number without using scientific notation. Okay, what would you do? And then what would that number look like? And write out this number in standard notation. Okay, go ahead and pause and take care of that. When you unpause, I will reveal. Okay, here's the reveal. We know that you're going to need to have enough zeros there so you can move the decimal 30 times to the right. So once you do that, you end up getting something that looks like this. And can we all agree how ridiculous that number is? It's got a total of 28 zeros, not 30 zeros, because you had 2 decimal places that you could move first. 2 of the 30 means you got 28 remaining decimal places that need to be added in, so we're going to crowd those with zeros until eventually we get to here. So when you do this, I mean, we don't do this very often, but when you do this, now you're going to have to verify that you've got the correct number of zeros. So you got 3, 6, 9, 12, 15, 18, 21, 24, 27, 28 zeros, 29, 30 total places. I can't even begin to think of what the name of this number is. So we're just going to call it 1.39. No, we're not. We're going to call it 1.99 times 10 to the 30th kilograms. That's good enough. All right, so scientific notation requires that one factor is a power of 10 and the other is a number greater than or equal to 1, but less than 10. So if you recall at the beginning of this lesson, let me go ahead and move this guy out of there for a second. At the beginning of the lesson, this is the algebraic form for scientific notation, c times 10 to the nth power, where c is any number, but it's got to be between 1 and 10, and it can be the number 1. So if you recall our inequalities that we graphed in 7th grade, having a circle around a boundary number and then shading it in means that boundary number is also a solution. So 1 is a possible number for that leading factor in scientific notation. 10 is not. It's got to be a number that's less than 10. So anywhere from 1 to 9.9999999, whatever, okay? Never a 10. So what that essentially means is this number right here, being a number between 1 and 10, is always going to have a single digit in the ones place. We don't want any zeros there. We don't want any digit in the tens place. It's got to be 1 through 9 in the ones place, and then decimal point, and then any digits to the right of it. Doesn't really make any difference there, although we often round it off to like the hundredth or the thousandths place for scientific notation, but still, that part doesn't matter. But this has to be a single digit 1 through 9. Okay? And then the power of 10 always has an exponent that is an integer. We don't want any fraction or decimal exponents. So scientific notation also uses the symbol x for multiplication instead of the dot. I think that's to keep you, well, they did it right there. I guess I didn't even catch that. But they don't want you confusing the dot for the decimal portion in that leading factor. So none of the numbers below is written correctly in scientific notation. So what I'd like for you to do is I'd like for you to copy each one of them down. And I want you to identify what mistake is being made here, and then fix the mistake and rewrite it in scientific notation. I actually caught one of the mistakes. I didn't catch the second one, so I'm going to adjust this right now and come back to you. And you can unpause, and when you do, that'll be fixed, and I will review. Alrighty, let's see how you did. So 25.6 times 10 to the fourth. What's the issue there? Well, remember, that leading factor, the C, is supposed to be a number between 1 and 10, and that's 25. So we would want to fix that. So how do we go about fixing that? Well, in order to fix that, we've got to think about this and the multiplication that's happening here. So 25.6 really is 2.56 times 10. And so if I just take this part and then move the power of 10 here and move that in with the other powers of 10, and that becomes 10 to the fifth power, right? 10 times 10 to the fourth is 10 to the fifth. So now we can rewrite this as 2.56 times 10 to the fifth. Two different problems happening here. First of all, we don't like having the 100 there. We want that to be a power of 10 written in exponent form, or in 10 to the nth power. So that should become a 10 to the second power. And also, they're using the dot. This is what I fixed instead of the multiplication x symbol. So we want to change both of those. And so it's going to end up looking like 5.46 times 10 to the second power. And then the problem with C is similar to the problem that we had over here. This is not a number between 1 and 10. So let's go ahead and think about how we can change that. 93 hundredths, we need to multiply that times 10 to get it to be 9.3. So I'm going to borrow one of these powers of 10 and move it in here. So I'm going to put these guys now together and change that to 9.3. And so it becomes 9.3 times 10 to the seventh power. All right, copy down these two numbers and let's put them into scientific notation. Now, my recommendation is to start by identifying what place is the leading digit in. Once you know what that place is, then you can rewrite this as a decimal number times a power of 10 that is not yet written as a power with an exponent. Okay, so 3, this is 370 million. So this number must be 3.7 times 100 million, right? Because that 3 is in the 100 millions place. Here, this is 48 billion 710 million. So that 4 is in the 10 billions place. So that would be 4.87. Ooh, did I forget the 1 there? Hold on. Let me put the 1 in too as well. We'll just put that in there. 4.871 times 10 billion. So go ahead and go from this step to scientific notation. Go from this step to scientific notation. I'll reveal in a second. All right, so this has how many zeros? 1, 2, 3, 4, 5, 6, 7, 8 zeros. So that would be 10 to the 8th. So that becomes 3.7 times 10 to the 8th. This has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros. So 10 billion is 10 to the 10th power. So this becomes 4.871 times 10 to the 10th power. All right, now let's do a little application here. Well, I guess this is an application. This is just reading numbers in scientific notation and comparing them. Scientific notation makes larger numbers easier to write. It also provides you with quick information about the size of the numbers. For example, Pluto and Haumea are both dwarf planets. I have no idea where Haumea is. Never heard of it before. Pluto has a mass of 1.305 times 10 to the 22nd kilograms. And Haumea has a mass of 4.006 times 10 to the 21st kilograms. Without even rewriting this into standard form, can you tell which one of these is the larger or heavier dwarf planet? And I think if we just, let me go ahead and get rid of that highlighting there. If we just focus on the exponents themselves. Remember, this is a number between 1 and 10. This is a number between 1 and 10. So when you multiply it times the power of 10, the number that's going to be greater is going to be the number that has the greater exponent. Because this is 10 to the 22nd, which means it's some number with 22 zeros, which makes it bigger than this number with 21 zeros. Right? Just like 1,000 is bigger than 100, or 10 million is bigger than 1 million. Adding that extra zero to this power of 10 is going to make this bigger than that. So just looking at the powers of 10 and the exponents, we can tell that Pluto is going to be the greater or the larger planet. Now, the same thing can be said for this. If I said 5.21 times 10 to the 27th and 6.08 times 10 to the 27th, I now can tell which one is the greater one by looking at the leading factor, because they both have the same power of 10, which means this one is going to have a 5 as the leading digit. This one's going to have a 6, which makes this one bigger. 6.08 is bigger than 5.21, so this one would have to be a larger number than this one right there. Okay, so if their powers of 10 and exponents are exactly the same, you just compare the leading factor. If these are different, then whichever one has the greater exponent is going to be the greater number. All right, which gets us to our last, and I told you this one was going to be much shorter. We're going to be done in just a couple minutes here. There are processes that you can do with scientific notation. Anything that you can do in standard notation, you can technically do here, although some of them probably would be a lot more complicated. Multiplying and dividing, you can actually do this with numbers in scientific notation, when it would be really, really horrible to try and do this. In fact, let me just do this right now. Can you imagine putting both of those numbers into standard form and then multiplying them? That would be a horrible, horrible thing to have to do. Your calculators wouldn't be able to handle it. You wouldn't want to write all those numbers out. So let's simplify it a little bit and let's just show the basics. Remember, these parentheses are telling you that this multiplication has priority over this multiplication. But all you're doing is multiplying. So technically, oh, stop it. Technically, it doesn't matter if the parentheses are there or not. It's not going to change anything. So let's go ahead and use commutative property and rewrite it where the 2 and the 3 get grouped together to make 6, and the 10 to the 3rd times the 10 to the 5th get grouped together to make 10 to the 8th. So now, what is 6 times 10 to the 8th? We'll add 8 zeros to the end of it, and it is 600 million. So we were able to take this original problem that was written in scientific notation and use what we know about exponent rules and commutative property to get an answer without having to do all the paper pencil or have to worry about all those zeros. Okay? The same can be said for division, although we have not quite yet talked about what it means to divide powers. Okay? So if you take 8 times 10 to the 15th and you divide it by 4 times 10 to the 2nd, we are going to learn that you can rewrite that as 8 divided by 4 times 10 to the 15th divided by 10 to the 12th. And 8 divided by 4 is 2, and 10 to the 15th divided by 10 to the 12th, trust me right now, it's 10 to the third. We'll get into the details of that later, which becomes 10 times 1,000, which is, 2 times 1,000, which is 2,000. Okay, so the basics of scientific notation. Please make sure your notes are good. If you need to go back and rewatch something to fully understand it, please do so. And we can talk about this in class. We're going to review the homework, and there will be some of these problems in the homework. So I think there might have to be a check for understanding for this too. Absolutely, we got to do a check for understanding. And there's going to be an assessment on this. So make sure you've got good notes and you understand it fairly well. All right.